Hi everyone, this is Yang from Virginia Tech. I present our paper, Session Key Distribution Made Practical for CAN and CAN-FD Message Authentication. Automotive communication networks are ubiquitous in modern vehicles for enabling in-vehicle communication between electronic control units or ECUs. In most vehicles nowadays, there are a whole bunch of different automotive communication networks. The most well-known of them is the controller area network, or the CAN bus. The CAN bus has been the de facto standard for the control of powertrain units or other safety-critical subsystems. CAN-FD is a 2012 extension of CAN bus. It can accommodate faster data transmission. Automotive communication networks are predominantly designed for optimized communication speed, but they are heavily criticized for their lack of security. Recently, there has been a series of high-profile attacks. The attacker gets access to the internal control of a vehicle. The attacker can eavesdrop, spoof messages with arbitrary content to critical ECUs, or simply knock off the ECUs. The root cause for this security debacle is there's no effective security mechanism at all in these protocols. In response to the security deficiency, the AUTOSAR Association, which is a global development partnership of automotive interested parties, has provided software architecture for future automotive communication with built-in security measures. They include entity authentication, message authentication, which guarantees the message integrity and authenticity and the resistance of replay attack. It also provides guidelines on crypto strength, such as the length of authentication keys and MAC. Notably missing from the specification is the establishment of session keys for the purpose of message authentication. Session key establishment is critical to the real-world deployment of any security systems and is also the focus of our work here. Prior to AUTOSAR, there have been many proposals on CAN message authentication, and some of them have addressed key establishment. There have been 3 paradigms of key management systems from the prior work, and only the second one key for each message ID, is AUTOSAR-compliant because each message subscribed by a group of ECUs, they are shared the same key for communication. As we will show later, our proposed key establishment protocol is a key distribution protocol because of the efficiency in communication and computation. We propose a key management architecture first. The system model consists of N ECUs and M message IDs. So the goal here is for all ECUs that subscribe to message J will get a shared session key SKJ. And to facilitate the real-world deployment, here we raise 4 practical requirements for the key establishment. First, it has to be lightweight in computation and storage. Second, it has to be efficient in communication. Third, AUTOSAR-compliant in terms of security requirements. It must accommodate for the on-demand ECUs, which are those ECUs who are switched on during driving, not from the start. We propose a new entity called key server in our system. Key server is kind of like a central entity in the system that shares a long-term key with every ECU. And at first, it generates a bunch of session keys from 1 to M, and it maintains a 6-bit system epoch. In the end, each ECU will get the session keys for the message it subscribes. To achieve these goals, we design key distribution protocols. First of all, we identify 2 primitives. The first one is KDC. The second one is SKT, which stands for secret sharing-based key transfer. And we adopt them for session key distribution in CAN and CAN-FD bus. SKDC is a baseline protocol. SSKT is our novel scheme, which achieves better communication efficiency. The baseline SKDC protocol, it works like this. In phase 1, key server generates the session keys. And in phase 2, KS delivers these session keys to the ECUs one by one for each session key. And in phase 3 confirmation, each ECU will send back a confirmation message to show that it has received the session keys it subscribed. KS confirm their receipt of the session keys and then move on to turn on the vehicle. Here comes our second primitive, SKT. The scheme itself is based on Shamir secret sharing. It assumes that each member I keeps the secret pair with the key server. So in the first place, each ECU sends a random challenge to the key server, and the challenges will be added to the Y coordinates as an offset. The session key and the secret points, the red ones, will be used to generate a polynomial by the key S. Key S randomly choose another T auxiliary points on the polynomial. At the ECU end, the polynomial can be recovered from the only secret the ECU has along with the T public auxiliary points. The computation can be done by Lagrange interpolation on these T+1 points. When it comes to using SKT in practical scenario, SKT has a clear advantage in communication efficiency because of its broadcast nature, but it also has a disadvantage. It's all about the finite field arithmetic. The finite field used is to be a product of two very large primes. It is used for resisting the insider spoofing attack, and the security relies on the intractability of large number factorization like in public crypto. So W should be very large, likely thousands of bits long. Is clearly impractical for resource-constrained ECUs. We adapt the SKT primitive into our scheme SSKT. For every 128-bit long secret key, it is dissected into 16 bytes, and every byte will be treated with its own polynomial. So in this way, the polynomial operation for each byte can be done within the Galois field 256. And secondly, to address the insider spoofing attack from the previous slide, we let the key server to generate random challenges and send it back to the ECU. SSKT works like this. The long-term key, which is kept by the key server and each ECU, is now a key pair. In phase 1, key generation, key server generates the two session keys. In phase 2 preparation, key server will randomize 3 challenges and send it to each ECU. The random challenge will be used by each ECU to derive its own random secret for polynomial recovery for each message ID it subscribes. And in phase 3 key delivery, first key server generates the polynomials accordingly, and then it broadcasts a KD message. Each ECU can recover the session key. So for every byte from 1 to 16, it interpolates the corresponding byte of the session key from the TJ auxiliary points, which is shown in the KD message, and its local secret, which is the long-term key pair. The Y coordinates has been offset with the random secrets. The session key for message J can be concatenated from those bytes, and this key can be verified with the MAC. And in phase 4 confirmation, key server verifies the confirmation messages and turns on the vehicle. So similar to SKDC, product message has to be sent in separate frames if the payload size is too large, and the on-demand ECUs can send a request message and can be accommodated for with a KD message. Both SKDC and SSKT achieves session key correctness, session key confidentiality, and ECU integrity and liveness. You can refer to the paper for more detailed discussion on the security. We implemented the 2 protocols for CAN bus deployment. So for each protocol, we provide a key server program and node program. The programs are written in Arduino IDE. Our code is available in GitHub. We made further optimization for SSKT for efficiency purposes. We use lookup tables to implement the GF256 arithmetic. Second, we let each ECU to pre-compute the Lagrange coefficients. So in this way, we effectively trade memory for speed. We built a test platform with CAN bus. In this platform, there are n ECUs. Each of them subscribes to all the m message IDs. We use Arduino Uno to simulate an ECU node, Arduino Duo to simulate a key server, and every board is attached to a CAN shield as a CAN protocol stack. We connected all the boards to a laptop to collect statistics. So here is the result. When m equals to 1, SKDC has a performance advantage, but when m equals to 6 and n is larger than 4, SSKT begins to show an advantage. And SSKT's advantage will continue scaling up for larger m and n. But here, the maximum n we can try stops at 5 because of a memory limitation of Arduino Uno. To circumvent the hardware limitation of our platform, we perform extrapolation analysis. First, we benchmark the runtime of crypto operations on the normal ECU, and the result below shows the extrapolated result of ECU computation workload in one protocol session. When Arduino Uno is used as ECU, SSKT begins to show advantage when M surpasses 12, and when Arduino Duo is used as ECU, SSKT shows advantage for all M values. We analyzed another metric, communication overhead. We first count the size of each protocol message in terms of CAN bits, and then we move to extrapolate the overall communication overhead for one protocol session. The result on the right shows SSKT has a clear advantage over Skdc in communication efficiency. Here we argue that because communication overhead is largely capped by the bus infrastructure, so therefore we consider SSKT's advantage in communication a highlight for its potential deployment. To conclude, we first proposed a key management framework for ECU message authentication, and then we proposed two session key distribution protocols, the baseline Skdc and a secret sharing-based SSKT, which has better communication efficiency. We implemented the two protocols and evaluated their performance with hardware test platform and also extrapolation analysis. We will continue work on the following issues of SSKT. First, how to achieve better memory efficiency. Second, how to accommodate for larger group size in SSKT because currently the group size limit is 128. We're going to do this potentially with larger finite fields as well as more efficient polynomial operations.